So China, Europe, India, Japan, Korea, Russia, and the United States, countries that you often see that are not perfectly ideologically aligned or even get into conflicts, trade wars, etc., have made a 40-year commitment that they will work together to build this single machine because they share a common goal about the benefit of industrial scale fusion being proven, demonstrated for future generations. And your preference is that I look into the camera or look towards you?
I think the camera would be better.
Okay. So, how do you describe fusion? Fusion is actually something that is why we all exist. It's the energy that powers the universe. It's at the core of the sun and the stars. But we've known that for precisely 104 years, 1920 when this was discovered. And we think of the sun as this gigantic ball of hydrogen gas, which it is, but it's so big, there's so much mass that at the core of the sun, the gravitation means that the density of the hydrogen there is about 70 times the density of steel. So fusion is happening because molecules, atoms, are being crushed together. And from that, you get this enormous amount of energy that eventually brings light and heat and life on Earth, or for all the energy of all the stars. The question is, what do you do to replicate that on Earth? And we have known about fission for a long time, where fission is a neutron enters a very heavy molecule like a uranium atom and splits it, and you have things that come out of that, including more neutrons that can go on as they slow down to cause more fission. Fusion is very different. Fusion is using hydrogen, like in the center of the sun, but we cannot artificially create gravitation. So the only way we can do that, well, we've come up with several ways to do it. One, inertial confinement puts a tiny little bit of a little peppercorn of fuel and hits it from all sides with lasers. So there you're maybe trying to simulate gravitation just by the pressure and the temperature of lasers to compress and release the energy. What we do at ITER and in magnetic confinement fusion is very different. We take a super large space. We use a donut-shaped space, what we call a tokamak. So in ITER's case, 800 cubic meters. And we put the same amount, just 2 to 3 grams of two forms of hydrogen, deuterium, which has an extra neutron, and tritium, which has 2 extra neutrons. And we release it into the space as a gas. And then we run a current through it. So as in a fluorescent light bulb, when you run a current through it, you create a plasma. The nuclei separate from the electrons and everything becomes a charged particle soup. And then you continue to heat that until you get to 150 million degrees, 10 times the temperature of the core of the sun, where the molecules are going, the atoms, the nuclei are going so fast, the charged particles, that instead of repelling, they actually collide and fuse. And from that, you get this gigantic burst of energy. It's still E equals mc squared, but a different way than fission, and about 4 times as powerful as fission. So that creates an incredibly powerful neutron and a helium nucleus, a non-radioactive helium nucleus, that still both have a lot more energy than the incoming particles. A little bit of the mass has been converted to energy, to a lot of energy. The helium can continue to act as a heating system because it still has high energy. And the neutron is the only uncharged particle, escapes the magnetic field, hits the wall, and hopefully transfers that heat to be harnessed. So what is ITER? The ITER is, in one sense, an international collaboration. So it's a gathering of 35 countries, now 33, with the UK exited from Brexit and Switzerland backing out of Euratom, that are focused on building a single device. But it is not like a collaboration where you just talk or a collaboration where you just send money. It's a collaboration where the countries are actually building the project together. So every country in ITER wanted to host the facility. And of course, that's not possible. So instead, they agreed that 80 to 90% of their contributions would be in the form of components. So China, Europe, India, Japan, Korea, Russia, and the United States, countries that you often see that are not perfectly ideologically aligned or even get into conflicts, trade wars, etc., have made a 40-year commitment that they will work together to build this single machine because they share a common goal about the benefit of industrial scale fusion being proven, demonstrated for future generations. So there are specific technical goals for ITER, and there are specific, well, some are actually just physics parameters, and some are so measurables, and some are more wordy. So we would generally say the goal is to demonstrate industrial scale fusion energy as being a feasible source of clean energy. So that would be the kind of stated goal. Within that, it means that we want to be able to demonstrate the integration of all the different systems that are required for fusion, which can be heating systems, cryogenics, robotics, the insane level of metrology to provide the necessary precision, the manufacturing. So all of these different things to be demonstrated. Very specifically, the goal reduces to either the term burning plasma or to the letter Q, which for physicists, Q for plasma physics means that across the tokamak, for a given amount of heating in, what is the amount of thermal power that comes out from fusion? ITER's parameter is 500 megawatts of thermal power out for 50 megawatts of heating going into the plasma. The burning plasma aspect of that is that if you, in the reaction, the outcoming neutron carries the heat to the walls, and the energetic helium particle that is produced serves as a heating system to continue to heat the plasma. If you can get to the point where the volume of fusion is such that you are actually producing 50% or more of the heat for heating the plasma from the plasma reaction itself, meaning from that helium nucleus, that's called a burning plasma. If you would get to the point where you actually could turn off all your heating systems and just keep adding fuel and fusion would perpetuate, that would be called ignition, like when you get to that point in your fireplace when burning wood. ITER will not necessarily, it might hit ignition, but we will certainly hit a burning plasma. So why is ITER in Provence, here in the south of France? Well, there are a couple of different reasons. You can look at the obvious ones, such as that France, right next door to us, is a big nuclear center, Cadarache, where the French government leads a lot of projects that range from a research reactor they're building, a lot of civilian nuclear power research, as well as clean energy research and some military aspects. But that was not it by itself. When the 7 members of ITER were asking who could host, it was the late 90s, early 2000s, and there was actually quite a bit of jockeying for who could host this incredible project. And the candidates, at one point, Canada had actually joined the project because they thought maybe they could be the host. They dropped out when that was no longer feasible. And then we had a point at which it came down to Europe or Japan eventually. And in Europe, the UK, which was part of Europe still at that point, had the next biggest tokamak, which was JET. Germany had W7X, which is like a tokamak but twisted. It's a stellarator, another fusion device. So it probably came down to France and Spain. And here I go into legend, because I cannot validate this specifically, but legend says that Jacques Chirac, the French president, got his foreign minister to go to Spain and say, we've got the FIFA World Cup coming up, we've got the America's Cup yachting race coming up, and we've got this thing called ITER. Can we agree that we shouldn't have one country that got all three? And so that sort of was a negotiation that said, okay, we'll take this thing ITER, without even knowing if it would be for Europe or Japan. And then Chirac was a Nipophile, a real lover of all things Japanese, very much loved with the Japanese prime minister. So Chirac went to Japan, and he said to the prime minister, your location is very remote at Rocca-Mura, and it's going to be very hard to get scientists there. Everybody will love to live in Provence, in the south of France. And so you have to let us do this. And the French, if the legend is true, the Japanese prime minister said, okay, but we can't announce it. And Chirac said, why? And he said, because it's 2005. George Bush still hates you for not joining the French joining the coalition to go into Iraq. So let me talk to George Bush and see if he would agree. So that's the legend as to why we're here in the south of France. So ITER will generate energy, but it won't generate electricity. This is a great question to explore because it's been at the heart of a lot of controversy. When you build a machine like ITER, if you look out, my window, you will see where the turbine hull would sit for a normal, say, nuclear facility or any kind of power plant. We don't have a turbine hull. We will have a giant heat exchanger. So it's got the absorption capacity of 1.2 gigawatts of heat. So it's a really large absorption factor. But ITER is a large experimental device, like a sort of national laboratory, but a convergent national laboratory for all the 30 plus countries that are involved. And so we will generate energy, but we will not attempt to harness that energy. The question that has been at the root of confusion is whether we will generate net energy. And the answer is absolutely yes, but across the tokamak, not in terms of the amount of electricity used to power the facility, as opposed to the electricity generated, which will be zero. So the generation of energy, yes. Net energy, absolutely. Net power across the tokamak, but not net power in terms of the balance of power across the facility. The easiest way to explain the safety of fusion is contrasting it to fission. It's not a chain reaction, so it doesn't have a buildup of heat that has to be carried away. So when fusion reaction stops, it just stops. It goes from 150 million degrees, 2 to 3 grams, to zero. So it's very safe. The physics reaction is safe. Sure, fusion will generate waste, including radioactive waste, but nothing that is long-term, highly radioactive waste. So instead of a complex fission reaction that makes a lot of different isotopes, some of which are very long-lived, fusion essentially will have two types of waste. There is tritium, which is generated, and most of that is recovered for breeding and use as fuel, but it can get into, there can be lots of tritiated metal, and the metal around that makes up the tokamak will, of course, become radioactive. But that's, if you choose your metals correctly, then that is all short-lived, which means 100 years or so, and you could recycle the materials. So you will see this question: why does ITER have 35 countries participating? What are some benefits that those countries get? And this question of 35 versus 33 is right in transition, because in reality, we still have major UK companies post-Brexit that are still engaged in the project, and some Swiss companies that are engaged. But Europe's membership in the project is through Euratom. And so when after Brexit and UK choosing to exit, and Switzerland, which was never European Union, but was part of Euratom, and Switzerland is backed out. So we have this 35 or 33. The question of what are the members' benefits actually comes down to why. It's a deeper question. It is, why is ITER unique in history? And I'll make that argument. I think after fusion was discovered, there were several decades where everybody was trying to figure out, how do we harness this? How do we take what the sun does and do it on Earth? And there were a lot of failed attempts until there was this Soviet high schooler who wanted to be a physicist that got conscripted into World War II and fought with the Allies. And after the war, he was stationed by himself on Sakhalin Island, and just a big stack of textbooks, no formal university education. He's the one that came up with the tokamak, and he sent the idea to Joseph Stalin, who had no idea, but gave it to Sakharov, his lead scientist, and they said this might have some merit. So they built this T1, tokamak 1. And by the end of the 1950s, now Khrushchev was the premier, and it was Igor Kurchatov as the lead scientist. They did something that I would challenge you is unprecedented in human history. They went to their Cold War enemies, the British, and made a presentation of all of this probably classified information. This is what we're learning. Why? Because what they recognized was this could have fantastic benefit for all of humankind. And of course, the Americans, the British were very suspicious of this, but science tends to be an avenue for diplomacy. And by 10 years later, when the Soviets had built T3, the third tokamak, they had reached 10 million degrees, which nobody had ever gotten to before. And they presented this at a conference, and they said to the British, come back to Moscow. You're better at metrology. Verify our temperatures. And fusion has been a collaborative exercise since that time. So how does that translate to member benefits? If you look at the tokamak, this circle, there's a US magnet at the center. There is an Indian-made vessel that goes all the way around the outside. There are Japanese and Italian made D-shaped magnets that go around. There is a Chinese made for Europe. China made a magnet, a circular magnet at the bottom. Europe made the next four, and then there's a Russian magnet at the top. And there are actually more than 1 million components. Most of those components were first of a kind, which means that the industries associated, the companies associated, had to do things that were unprecedented. And from that has come innovation. And there's the genius of it. ITER's innovation is shared, which means that there are, from our work on magnets, there's a company, an Italian company, that's done the most advanced mapping of the human brain. There are benefits in transport, in pharmaceutical, in electrical grids, in manufacturing, in industry. If you look at the very bottom component, the first major component that was installed at ITER, it was the base of the cryostat. If you got down there to look, you would see all these welding lines. And that's because India could not ship a 30-meter component by air or by sea or by land. So they sent pieces from a terrific facility in Hajira. And here on the ITER site, a crack team of German welders under Indian supervision, under European, using European steel, under French safety regulation, produced this component. And at 30 meters, it fit with a precision of less than 3 millimeters at every metrology point. And that's just sort of a metaphor for how these benefits of working together really come out. The companies become a fusion supply chain. They have spin-offs into other directions, and each of the members involved gains knowledge in how to build the power plants of the future. So if you think about the challenges of international cooperation on something where you're constructing a device together, you have, of course, the obvious political challenges. When you see the flags on the work site, China is flying next to Europe because it's alphabetical, and Russia, the Russian flag is flying next to the United States flag. And it goes without saying, I don't have to go into detail about the how you see trade wars, India's wars, trade wars with China, or insecurities or distrust or whatever. So politics is there. That's a challenge. But if you're building something, the challenges are greater because we don't necessarily speak a common language. So we have to find the common languages of computing, of CAD drawings, of how we do diagrams, etc. Every country involved has got incredible technology expertise, but they all do things a little bit differently. So program management, etc., has to be done in a sensible way. If you walked into the assembly hall, you would hear Mandarin, Russian, French, Italian, English, because these are the companies now doing the contracts that are doing some of the assembly. So that is a challenge. I think the longevity of the project is a challenge, and the cost of the project is a challenge. We have to take that cost back to the members and ask for them to continue to spending the budget, including times when the project is delayed, and so it's going to cost more. But we have had very good success with, I think, members recognizing that benefit. A specific challenge, of course, would come with something like the war in Ukraine, where we got a lot of challenge from diplomatic circles saying, why are you still keeping Russia in the project? Because they didn't understand the challenge. And the answer is very simple. The ITER agreement is, the ITER is a project of peace. And the ITER agreement anticipated this very long channel of working together for a common future. And you can ask that question about any particular war, whether it is actually a physical war. And of course, that's something we don't want, we don't support, we hope it can be solved peacefully. But we also recognize that as physicists, we think in, time-space continuum, we are fighting another war altogether against climate change. And that can also cause misery, death, lowering of lifestyle for future generations. And we share that common vision. So that is a very clear answer. I give you one more, which is think about COVID. If you look at COVID, ITER was going into assembly, and we decided to continue. But the nations of the world at that time were thinking very desperately about the projections of the epidemiologists. The best projection in January of 2020 as to how long it would take to get a vaccine was 4 years. And the economic impact of that was so intense that the countries of the world spent the equivalent of $94.5 94.5 billion US dollars. Easily 3 times, 4 times the cost of an ITER project. But they did it in segments. Now, the miracle was that 9 months later, you had 7, 8 vaccines and of different benefit, but the worst of them would have been a godsend at the beginning and considered a miracle just 9 months earlier. So that was an example where had that money been invested cooperatively, because we faced a global pandemic, it could have been done probably with a lot less funding and only a few vaccines coming out, but then shared equally all along. So ITER provides a model for how to address problems that transcend ideological and national boundaries. I think that it's safe to say that ITER is the most complex science experiment of all time, both because of the amount of first-of-a-kind components, and then also because of all of the different not just the engineering and science challenges, but the complexity added by all of these countries working together to produce components in thousands of factories on 3 continents and shipping them here for unified assembly. But there's also the question that comes up: is ITER the most expensive science project of all time? And there's this phrase, in the world, because if you say in the world, the International Space Station has hit, I think, 120 billion, and ITER will never get anywhere close to that. But it's also interesting to look at the escalation. So ISS started as about 4 billion as an estimate, went, I think, eventually by the time it was launched to about 16 billion. And then it kept escalating, and eventually it got to about 120 billion. So ITER's costs have also risen from original projections. Some of those original numbers were always very round. They were political numbers because they said don't spend more than 10 billion or don't spend more than X. So yes, the costs have gone up. I think if you were to look at not just science projects, but something like the high-speed rail system in the UK, HS2, that was originally projected to be in a 35 billion pounds range. And then it went up to like 70 billion pounds, only a matter of maybe between 6 and 8 years later. And then it has come down because they've cut out scope. But it's another project that would be probably more expensive than ITER will ever be. Is it a science project? Not exactly, but it's a sort of project of comparable complexity where you start to apply new technologies in ways or locations that have not been done before, and it escalates in cost. So in a certain sense, when you ask this question, when will ITER be ready, you have to define ready. And it will take still quite some time, I think, for us to deliver on all the possibilities of the experiments. In a certain sense, you could say we're ready now, because when ITER was conceived, we were naive. We thought of a timeline to do a very long project that would demonstrate feasibility of fusion, and then a demo project that hopefully many of the countries would join as well. And then we would start telling everybody how to build these fusion plants. That's not what happened. In fact, the benefit of ITER right now, the readiness now, has been evident in the rise of private sector companies for whom the CEOs tell us investor confidence that fusion can be done has gone up because of ITER demonstrating that these components could actually be built at scale, and the breakthroughs in engineering and so forth. So we have seen roughly $7 billion, US equivalent dollars, invested in now, I think it's about 45 private sector fusion initiatives. So that is a certain sort of readiness it is now. And some of them want to embed their employees with us to learn about assembly and so forth. Second answer, when ITER is ready for its first operation. We've just gone through what we call a rebaselining, a cost and schedule estimate, that exercise here. We have presented it to the ITER Council, and we are now using that schedule as a working reference. There are still some discussions about it and so forth in terms of acceptance or approval or some other method of how we go forward. But under that schedule, there's a big contrast from the last one, which was 2016. In 2016, we envisioned getting as fast as possible to what we call first plasma, a closed machine, any plasma possible, and then immediately shutting down and doing more development over 4 stages to the middle of the 2030s, when we would launch what we called full fusion power. The new baseline is taking advantage of the delays, so to speak, because of those delays, more components are available to build a more complete machine. So we will actually do that assembly and launch the first plasma, if you want to say that the initial plasma operations will take place in 2034, but it will be immediately followed by 27 months of substantial research, because the machine will be ready to demonstrate the integration of all the components, simulating the full heat loads, all of those kinds of things. So there will be really substantial research returned then, and then we will take out sort of the temporary barrier first wall, put the permanent first wall in, do some more assembly, and the start of deuterium-tritium operations phase will start in 2039. And that will be the even more substantive sorts of experiments that go on to return to provide the return on investment. So to really understand the role of fusion in global energy markets of the future, we need to take a step back and stop criticizing fossil fuels until we first understand what they did for us. The beauty of fossil fuels and why they were fueling advanced progress in civilization for the last 120 years, 150 years maybe, is that it's very versatile. You can burn kerosene in a lamp. You can make it as your light. You can drive your car on petroleum or diesel. You can make a gigantic baseload power supply. The problem with it is that our waste receptacle was the atmosphere. But now you say, what role does any clean future energy source have? And what we have with renewables is terrific when it's a distributed low power source, like powering a home, powering small cities, industries, etc. But it's very challenged when it comes to using solar or wind or anything else in a renewable energy to power Tokyo, or without the appropriate landmass to do it. So what fusion gives us is a complement to renewables for the baseload power supply. If we want to go to electricity as an end use, or we want to go to hydrogen, which is not a fuel, but is a great carrier of it, it can be a great energy storage capacity. It can be used to power, say, well, many applications actually that hydrogen can be used for. But you have to make it. So you have higher electricity demands to make the hydrogen, so less efficiency. Fusion provides you in a future energy market with the baseload power supply that renewables struggle with. So it's a great complement to renewables. You would envision a future in which fusion, because of its higher safety, better safety characteristics, could be placed closer to a city than you would do, say, for a fission power plant. It can, in theory, if you go far into the future, fusion is a feasible driver of very, very long-term space vehicles, space discovery. Fusion has a lot of characteristics like that, if done at the proper scale and so forth, can be very much a complement to renewables. So there's a great question that people ask as a matter of civilization. It's a very old question. Why should a tribe, why should a nation invest in science? And I was recently at a gathering where a colleague, a professor and department head at a university in Munich, talked about his work on looking for exoplanets. And somebody asked the question after he was done with his lecture, why are you engaged in useless research? And in a certain sense, it was a joke. In a certain sense, it was very serious. And I think there are two fundamental reasons that come from that. One is that the theoretical science produces discovery that tells us more about our place in the universe and about ourselves. And it elevates our thinking as a race. It inspires us. But there is another much more practical reason, that is, you get applied engineering, you improve the quality of life through the technological applications, innovations that come out of that basic science discovery. So CERN isn't nearly as practical in its stated outcomes as ITER, but discoveries at CERN have led to the launch of the World Wide Web, which is a pretty basic benefit for it. Has changed everything about how we interact as humans. It's changed finance and travel and many, many other things. So, and brought us together as a human family. So the conjunction between the the benefit of basic science, which elevates us and inspires our kids, gives them careers, leads us in new directions, often conflates with and brings out unexpected results. So at ITER, we have both basic science and advanced technological innovation working together towards stated goals. But some of the benefits that come out have nothing to do with those stated goals. You're doing work on electromagnetics, on cryogenics, etc., and you're trying to make fusion feasible. And the result is benefits in brain science, benefits in proton cancer therapy, benefits in less loss of electricity because you can use high temperature superconductors for long speed transport of electricity, or transportation benefits for levitating trains. There are literally dozens of unexpected benefits when you engage in basic science and in advanced technological innovation.